Let's talk generating functions. In particular, probability generating functions. There are other generating functions. The main one, if you're doing probably the higher or the further version of the stats module for whatever exam board you're doing, you might encounter moment generating functions as well. That will change a little bit. But here we have probability generating functions. We've got gx of t is k ln 2 over 2 minus t. It needs to do a bunch of stuff. Find k, find the variance, find the probability. Easy peasy. But first, let's remind ourselves what a generating function is, or a probability generating function is. So gx of t is the expected value of t to the x. Okay? So that's going to be useful, that idea for us. But what does that mean? Well, expected value of a function of x is the sum of the probabilities times that value. And I'm going to write a few of these out because it does illustrate a good point for me later. So for example, this will be, I'm just going to go P0, hope you don't mind that too much, T0 plus P of 1, T to the 1, plus P of 2, T2 plus P3, T3, etc. All right, that's really what's going on under the hood here. And we can get all kinds of good results out of this. Now, in particular, before we go any further, let's have a look at part 1. Let's have a look at part 1. Well, what would happen if I plugged in 1? Oh, look at this, clean black pen. So what if I was to plug in 1? Because the key for this is, of course, is that 1 to the power of anything is 1. 1 to the 0, 1. 1 to the 1, 1. 1 to the 2, 1. So this just becomes the sum of the probabilities. But this is a probability distribution, so the sum of the probabilities needs to be 1. So my probability generating function evaluated at 1 needs to come out as 1. So let's pop that in. K ln, it's a terrible ln, but I'm going to leave it there. 2 over 1 is 1. So that tells me that k is 1 over ln 2. Smiley face. Write that down on a piece of paper somewhere, the 1 over ln 2, not the smiley face, because I'm not going to write this every time. I'm just going to do the rest of it in terms of k's. Please don't hate me. Right, find the variance. Well, here's another cool thing we can do with generating functions. So let's have a look at this guy here. I can differentiate it. If I differentiate this with respect to t, this is just a binomial. Now, I can differentiate inside the expected value. So this becomes the expected value of x t to the x minus 1. Why might you want to do that, I hear you say? Well, what if I did this? Let's do this again, and then we'll have a little look-see. Let's differentiate it again. That is the expected value of x, x minus 1, t to the x minus 2. Well, the usefulness here is that, of course, if I plug in 1, 1 to the power of anything is, again, e of x. And you can try that out here. It will pop out. All right? It'll pop out. So if I plug in the 1 here, that just becomes e of x. And in the same way, the second derivative evaluated at 1 is e of, if you expand that, x squared minus x, using what we know about expected values, that is e of x squared minus e of x. Okay, so what does that tell me? Well, we're going to need to differentiate this bad boy, actually. We're going to want to differentiate it, which means you might want to rewrite it slightly. I don't like the look of differentiating that. I do not like it at all. No siree, Bob. No siree, Bob. I'm going to take a little bit of space here. Sorry, part A, we've already solved you, so you're no longer fun. That is k ln 2 minus k ln of 2 minus t. If we just use our rules of logs. So, g dashed of 1, g dashed of t is k over 2 minus t. And if I differentiate that again, I will get k over 2 minus t all squared. Am I okay with that? Power of minus 1. Pick up an extra minus 1. Yeah, I think we're all good. Let's plug 1 into this. So e of x is, well, k over 2 minus 1, which is k. And here, let's plug 1 in to give ourselves this, e of x squared minus e of x. That is also equal to k by plugging 1 into there. Right? K over 1 squared is k. But this, combine them together, you get e of x squared is therefore 2k. Because of course we just established from here that e of x is k. Therefore, var of x is e of x squared, 2k, minus e of x all squared, k squared. Remember, k is 1 over root 2. 1 over root 2. 1 over root 2. Yep. Just checking my little crib sheet. All right. So, 2 different applications of it already. How about we use the probability generating function to generate a probability? Now, this comes down here. I'm actually going to do this here, because what we could do here as well, let's think about differentiating this term by term rather than the bulk differentiation I did here and here. This is a constant, so it disappears. P1 times t just becomes p of 1. This becomes 2t p of 2. It becomes 3t squared p of 3. It becomes a 4t cubed p of 4, etc., etc. So the nice thing is, for example, is if I was to plug 0 into this, that term goes, that term goes. Any term that isn't a constant term disappears if I plug in 0. Well, let's differentiate again. That goes away. I get 2 p of 2 plus 6t p of 3 plus yada, 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 yada. And finally, differentiate a third time, I get 6 times the probability, let's write it properly, that x is 3. So you get 6 times the probability that x is 3. So what we are going to want to do is differentiate a third time. And this is how the probability generating function generates probabilities. You keep differentiating it and plugging in 0, and you will start getting your probabilities coming out. So G, part C, triple dashed x of t, where was I? Aha, here. I will get 2k over 2 minus t cubed. So G triple dashed x at 0 is 2k over 8, and that is equal to 6 times the probability that x is 3. So that tells me that the probability that x is 3 is k over 24. Which is, what we say k was? K was 1 over ln 2. There you go. Really cool. Love me some generating functions. I think they're an awesome bit of probability and maths in general. And it's how we get all kinds of cool results, like the central limit theorem, like many, many other things. You can do all kinds of absolutely bonkers things with them. So there you go. If you enjoyed this, drop us a subscribe, drop us a like, drop us a comment. Let's feed the YouTube algorithm. Hit the notifications so that you don't miss one of these as they come out. I'm Nick. I hope you found this interesting. I certainly enjoyed doing it, and I will see you next time.